Greetings, welcome to another video. And I haven't posted anything for a while. I apologize about that. And also I noticed some of the comments didn't go through. I'm going to have to look and see if there were any others. I don't know why that happened. I thought I had everything with the regular filter. Maybe I'll even get rid of that. But sorry if your comments didn't go through. I'll see if I find any more of those. So here's one reason why I haven't been posting is I wanted to do a 6-magnet rotor, and you know, it's supposed to look more like that, and wake up the next morning it looks like this. And then this was a bad one because these things take like 8 hours. Made it all the way to there and then crapped out at the end. Then I got this one and I was all happy for a while, and then I went to spin it and it's doing this. I'm like, oh, you know, what's going on with that? And I'm thinking, you know, is this not level? Is the tape like at an angle or something? And you know, I kind of noticed, well, this magnet doesn't go all the way in, but this one goes all the way in. And then let me see if I can show you here, if you can see it. See, it's thinner there, it's thicker there. So even this one, although it held together, it didn't make an even print. So I'll stop complaining about that, except just to say that, you know, I don't know whether it's because I don't know what I'm doing with printing, or maybe because I have the entry-level ender, and so it's just not that dependable. But it's a shame because for me this is starting to get interesting, and what I'll do this time is I'll like spin stuff first, and then we'll go through the spreadsheet at the end. But you know, here we had a 4-pole rotor. Here you have a 6-pole rotor, and I have it set up all monopole. Later I'll set it up as bipolar, north-south, but now it's all just north facing up. So what are some differences that you're going to see here? Well, one is the duty cycle will be different, right? So let's say it's on for, you know, the width of the magnet, then it's off, and then on the width of the magnet. So the duty cycle is maybe 25%. Here you can see you could probably fit about one more magnet in there, so the duty cycle is 50%. So pulses more frequently, goes faster, but you're drawing more current because the duty cycle is higher. Now, as the coil goes faster, there is the reactance, so that tends to bring the amp draw down a little bit. It'll also have a little bit more torque since it's not off as much, and it weighs a little bit more. I mean, it's not like there's a 10-pound flywheel on here, but it weighs 50% more than this one. So there, I'm just giving it a spin, and you can see the wobble that I'm talking about. And what I noticed is, you know, anything up above like 1,000 RPMs and the thing starts barking. You know, you got this thing starting to do that. So basically it sucks. But it was good enough to gather some interesting data. And I'm going to go over that because some of that I found really fascinating. I don't really know everything that's going on with it, but some of it I found very interesting. Now you'll notice I'm going back to this coil, and you know, we had a lot of thoughts and discussion on, you know, why is it slowing down with the big coils it's brought in? Is it seeing the other end of the magnet? Is it unbalanced because there's not another one over there? And I'll tell you, I said I like this channel Monroe Live because they just tear down. Well, I'll show you. So I've been following this Monroe Live, and he does a lot with the new cyber trucks and, you know, all that. But if we, where is it? If we go to one of their most recent videos that I just watched, it is this. They have an electrical engineer that works there. I don't want to play this because I don't want to bother them. But we can just kind of take a few snapshots here. I think that falls under fair use. So they have their electrical engineer here discussing the strengths and weaknesses of induction versus permanent magnet motors. And the part that was interesting, well, the whole thing was interesting, but there's one part, if I can find it, you know, he's going through, there's some of the the way they design these things, and it seems to be a little bit geometrically like you'd expect with a window motor setup, which I found interesting. Introduction, let's get past that. A little further. Here we go. Strengths and weaknesses. So the induction motor, lower cost, this is the interesting one. Low spin loss, and then lower torque, lesser efficiency. Permanent magnet motor, higher efficiency, higher torque, costs more, higher spin loss. So I had to look that up because that was a term I hadn't heard before, is what is spin loss. And then he goes on and describes it, in that when you're freewheeling with the permanent magnet motor, that the permanent magnets moving past the coil of wire generate a back EMF. They generate current in here. And I actually made a video on this. I said your drive coil is a generator coil. And so it's like, I'm validated. I was right. Whenever it's freewheeling, it generates a current. And that current is actually, well, the magnitude of the direction of the magnitude of the magnetic field is in opposition to the spin, hence spin loss, and the current is in opposition to the current that you're feeding in. So it actually wants to feed current back, but it's back EMF, so it never gets above the input voltage. And just, as confirmation, if you go back and look at that where I'm saying your drive coil is a generator coil, if you have a setup like this, you spin it at 8 volts and then you turn it down to 4 volts, you'll notice on a power supply it doesn't go down to 4 volts. It goes down to like 5 volts, and if you have an amp meter hooked up, you see the amps go negative. That's because your back EMF now is higher than your input source until the rotor slows down enough and whatnot. So I'm kind of throwing the other stuff out the window because I think it's pretty obvious now. That's why the rotor slows down and amp draw goes down as you bring the coil in closer, is you're getting more back EMF. And, okay, that's fine. I'm fine with that. If you're using less current, but you're still closer in, so whatever magnetic field you make is going to be positioned better to drive the thing, then whatever current you are using is being used more efficiently. So I've gone back to a big coil. And I think that kind of gives a good explanation there of what's going on. It's a back EMF. And just last point is that's in contradistinction to the inductive spike, where you've seen running it at 4 volts, and there's 80 volts across the capacitor. And I was putting in I put in like a 1K, or rather 10K or 100K ohm resistor, as I was seeing, well, it just always seems to go to 80 volts. So no matter what I'm doing, I'd hardly ever change it. And then I realized, there's, it's an 80 volt switch on the solid state relay. So it's just bleeding over. It's going across the spillway there. And fortunately, I didn't fry the switch. But that's why it was always going to 80 volts. Who knows what it would really go to. This is where an oscilloscope would be nice. But it is pretty incredible when you think about it. I mean, 4 volts, and I'm just always hitting 80 volts. It's higher than that. And so I have to put some resistance on there just to see how the thing behaves in different situations. Okay, so here I spun up the contraption just at 4 volts. And you see it's wobbling all the heck over the place. Even at 4 volts, you can kind of see that thing starting to not want to stay steady. And here's a meter on what we're getting out from the spike. Here's an amp meter. We've got that one, but this one's a little more accurate. And then what I was also doing was putting either 1 or 2 pickup coils and then measuring that there. So really, I mean, what's entirely different with this motor is that you can have your generator coil, but then you also have this that you draw off, and when you draw this off, it doesn't affect the the mechanical efficiency. If anything, putting a little resistance there improves the mechanical efficiency and torque of this. So if you were an electrical engineer or something, it would probably be pretty straightforward to, all right, you get that and you add in that. For me, I'm just kind of flying blind, but that also makes it more fun, although, as I said, it's kind of getting frustrating because I'm seeing some interesting stuff now. So the way this behaves with the spike is, we've talked about the air gap, and I'm comfortable now with going with as narrow an air gap as I can. Then, so that's the y-axis. Then you have the z and the x-axis. Now, sometimes I was just moving the coil around and keeping the sensor constant, but another thing you can do is, if you move this out there, then there's your Hall effect sensor. That moves it further away from the magnet, and so that gives you pulse width modulation, a really simple way of doing pulse width modulation. You could also do that by setting the sensitivity of the Hall effect in the software, but that's a pretty straightforward way of doing it. And I mean, this is kind of interesting. The amp draw is dropped down to 10. We still got that spike, and then you can bring it in, and the amp draw goes up. I haven't played around with that too much yet, but it's a bit more efficient with the more narrow spikes. But that's not the main thing I've been looking at. Now the other thing would be like moving the coil here or there, which would be moving this in this axis. So this is where it's, I got no idea. It's just cool and interesting, and I'm just going to follow it along. Not to interrupt the narrative here, but that's my most recent print. And the problem is I don't know what I'm doing wrong. I don't know if it's a problem with the printer or if it's a problem with me. But back when I was younger, in high school and college, if you wanted some money, you might just, you just look for like temp work. And so I was doing like a week of temp work. We were stocking Toys R Us, the warehouse at Toys R Us. So you're just moving boxes all day. And I don't know whether it was a program or if the kid just answered, but he was obviously, he was kind of mentally retarded. And I think it was sort of a program. And so you get started early in the morning, you have your coffee or whatever, and you start like going with the boxes, and it starts to get like boring and sweaty. And he looks over at me, "What is the meaning of furious?" And so I'm thinking, well, that's different. This could be a bit of a long day. But the rest of the day went fine, and it was actually a very appropriate commentary. So looking at this, I remember his commentary. "What is the meaning of furious?" He said it just like that. All right, back to this. So we talked about the y-axis. We've talked about the z-axis, where there's two things going on. If you just move the whole machine and leave the sensor where it is, then you're changing the pulse width, and you're also changing the z-axis here. Things are really interesting on the x-axis. So if we move this there, we get that, and it changes the amp draw. We move it there, you get that. This is looking at what's coming out of the spike. Even a little more, and you see the amp draw is going way up. Now the problem when you start going here is the rotor starts slowing down. So when it was up there at like 20, it probably wouldn't even spin. But there's a point where you get the highest spike there, and even though the amp draw has started to go up, the percentage that you're getting out as compared to the percentage that you're putting in is greatest. And that's kind of neat. But there's a second thing that's going on here. Well, before I get to that, I'll just say that spot where you have the maximal spike as a percentage of your amp draw, even though the amp draw is going up, is not where the rotation is fastest. So the rotation is slowed down a fair amount, like 20-30% when you're there. And then you can put it in another place where you're not as efficient in terms of what you're getting out here, but the rotor's spinning faster and you're drawing less amps. So I found that really cool and interesting. There's another thing, though. This is what I was going to say a minute ago. When you're at that spot where the spike is doing pretty well and the rotor hasn't slowed to a stop, but it's slowed down a bit, as the rotor speeds up, the spike gets higher. When you're at the spot where the rotor's spinning fastest, and it's not as good there, but your amp draw's gone down, as the rotor speeds up, what's coming out from the spike goes down. So what's really cool about that spot, even though it's not that efficient, and I'm not going to set this up for you now just because it would take too long, but as I think I was saying, is I had one pickup coil, two pickup coils to have a certain, some resistance or even more resistance. And you can have it at a spot where you put in the resistance and you draw some off into a pickup coil. The rotor slows down, the amp draw goes up, the spike goes up, the efficiency of how much you're getting out from the spike as compared to the input is the exact same, and now you just add in this, and then you slow it down more, and it's basically the same thing. The efficiency of what you're getting out, because the spike's going up, but as it slows down, the amp draw is going up, so that stays sort of constant, but then you get a bit more out here. Now, again, as I said, I don't know what I'm doing with all this, so it's terribly inefficient, but I'll just show you now on the spreadsheet rather than like trying to go through each like, here I did it this way, here I'll just show you the data. So just bear with me, because this might seem kind of boring, but it got interesting for me. So here's your input. You got, say, 4 volts, and you end up drawing 15 milliamps, so your input is 60 milliwatts. And then I was saying, you can get all kinds of different spike voltages out. So here's one, spike voltage is 3.8 volts. RPMs are 594. Now, we know the voltage that shows up here, and we know the resistance that's here. So V equals IR, I equals V divided by R. So we can solve for I, the current. And that's what I'm doing here. D5 divided by 10,000 gives you the current. And then you take the current and times it by D5, which is the spike voltage. V times A equals your watts out. So you're getting 1.44 milliwatts out, and you're putting in 60 milliwatts, so you're getting a whopping 2.4% back. Whoa. Now over here you have voltage just freewheeling with one pickup coil or a second pickup coil. The second pickup coil is smaller, that's why those didn't double, but they were in series. And then when you connect it across a 100 ohm load, 0.534.693. Now the rotor slows down, right? Because it's loaded now. Because the rotor slows down, your spike voltage changes. And here it's set up where it's going upwards. And so now you do the same thing in terms of the spike voltage versus your new milliamp draw, which is now up to 20 instead of 15. Your new RPMs, and so And now, look, with it loaded, instead of getting 2.4%, because the spike voltage went up, even though the amp draw also went up, you're getting 2.7% back. And when you calculate it out, you're getting another 3.5% from the pickup coil. Now you load it more, you're getting 2.9% back and 4.6% from the pickup coil. I probably should have ran with this one some more. I don't know why I did. I think this one was a very short pulse duration, but then here's one again at 4 volts. Now the spike voltage is 6.9. You're getting 7% back. Hey, I mean, but it is like 2.5 times better. I have no idea, but for some reason I guess with this one, it was because as it was loaded, this was going down, even though overall you're improving because you're adding in the generator coil stuff that you're getting back. But I thought it was really cool when you slowed it down, this did better, which it did there. So here, I don't know why I picked this one, and I think this one might have been really interesting to run along with too. So here's your first one at 4 volts. So it was 4 volts, and you're drawing 22 milliamps, 88 milliwatts. Spike voltage is 6.3, RPMs are 654. That's what you're getting out from the spike, and that's 4.5% of what you're putting in. Here's your freewheeling voltage from 1 or 2 generator coils. That's 1 or 2 generator coils loaded. Now the spike voltage with each of them loaded goes up 6.3 there to 7 to 7.5. The milliamps goes up. The efficiency with one coil, 4.7, versus 4.5, 4.3, 4.4 versus 4.5. So it's about stayed steady, and you're getting 3.6% or 4.9% back from the generator coil. Now where it started to be more fun was here I went to 5 volts. So 5 volts, 24 milliamps, 120 milliwatts in, 8.5 volt spike, 796. Now you're getting 6% back instead of 4.5% back. Everything else was the same. And again, you load it, and 6.1 or 5.78% back. And even this is doing better, which is kind of curious. 4.2%, 5.79% back. And then 6 volts. And 6 volts, where are we? 6 volts, you're getting 7.6% back. So let me highlight these. So if we look at what's coming back from the spike as compared to what's going in, that's it at 4 volts, 5, 6, 7, 8, 9, 10, out to, I went out to 12 volts. And now you're getting 17% back. So, I mean, it's still not very good, but that dependence on voltage, I've done a fair amount of just like pulsing a coil on the desktop, and it's not that dependent on voltage. It gets better with voltage, but it's not like you go from 4 to 5 and you get a 1.5% improvement. And what's really odd is 1.5% improvement, 1.6% improvement, out to 7.6. About 1.6 or 7% improvement, 1.4% improvement. It seems to be like 1.5% or more, 15.1 to 17.2. So that's 2%. So like 1.5% or more for each stinking volt. And especially, you would say, well, here you're changing voltages, 4 to 5, like a 25% change. Whereas from, 11 to 12, percentage-wise, it's much less, but that is still holding there. So that's none of this is behaving like, just pulsing a coil on the desktop, and that sensitivity to voltage is profound. And so another curious thing here that I don't have an answer for. So I mean, this is really, I thought, a pretty dramatic change. And then here is what you're getting out. This is with the 2 coils, so the most loaded version. What you're getting back from a generator. So 5%, but it went up 5 and then 6.2, 6.5. I have no idea why that would happen. 6.6, and then it stayed there, and then it started getting worse. But then I kind of geeked out because, as I said, this rotor is 3D printed crap. It looks all right, but it's wobbling all over the place. So once you get it up, 1,400 RPMs, and so what you can do, let's see, how the hell did I do this? Okay, so 4 to 5 is 1.2 times more voltage. Well, I should have maybe added in the amperage, but just looking at it with voltage, 1.2 times. And then I have the RPMs went from 654 to 796. So that went up by 1.2. That went up by 1.17. So this went up 20%. This went up 17%. So 17 divided by 20 is 87. So for the amount of voltage you put in, 87% of it got translated into increased rotational speed, and then 82, and then 71, and then outlier there's 77, 66, 68, 63. And that's where, when I was running at 1400, I mean, the thing just sounds like crap, and even more so there. That's why this trend stopped. But I don't know why that trend is there in the first place. But you can see that you're not getting more rotation for more input here, because it's less and less is translating. But that's neither here nor there. I mean, the most interesting thing, and going from 4 to 12 volts here, is this 1.5% increase continuously from 4 to 12 volts. So there you're at 17.8. So, somewhere at 90 volts, then this will be greater than 1, except for this thing will fly the heck apart way before then. So now one thing is to improve that, and that's it's not impossible, but I would say, with this particular setup and this form factor, I'm not really sure how. I mean, one thing I don't have a clear handle on is wire gauge and what this does with different wire gauges. But you'd want a bigger, if it behaves anything like pulsing on the desktop, you'd want a big coil. And so you'd have to kind of start the design over. So I'm not sure what you can do too much to improve that, except for the air gap will change it some, although I don't know whether it'll make it better or worse. But we can work on this end, because these two are added together, so you're not really at 19% or 17. You're at 21% back. And while I'm not an electrical engineer or an engineer of any sort, I mean, I know that you can do a bit better than 6% back from a pickup coil. So this is an area where you can have improvement. So let's talk about that for a moment, and then I want to point out one more weird thing on here, and then I'm gonna hopefully not bang my head against the wall, just trying to get some good prints. Well, very first thing I say is, I mean, here was the same setup, but we were starting at 7% back instead of 4.5% back. And I haven't run that along with voltage. The reason being that it's starting to go down, even though you're doing better with that, with when you're loading it. And I just thought it was cool that it wasn't going down, the amount you get back. But I don't know what this does. I mean, maybe as it goes up in voltage, this goes from 7% down to 1%. Or maybe it's, instead of a 1.5% improvement, it's a 2 or a 3% improvement. So that's worth looking at, and I can even look at it with this crappy rotor. So that might be something to do. But if we talk about how do we improve this, because I mean that, again, I'm not an engineer, but I'm even just embarrassed as a non-engineer that you're only getting like 5% back. First thing is make a good rotor. Now that will, hopefully it won't start barking until like 2,000 or 3,000 RPMs. So that will let this trend continue. That's the first thing. The second thing is I can drop the air gap even more. And right now, if I try and drop it further, it starts bumping up against it because this rotor is not even. And that might seem like a small thing, but it's not a real big air gap. And if you could cut that in half, we're using air cores now, so you don't have to worry about the iron clogging or anything like that. And I'm convinced now with air cores, the smaller the air gap, the better. So what I'm saying is your amp draw will go down, the rotational speed will go down, but the amps that you're getting through will be more efficiently driving the thing because the magnetic fields are closer. And recall that the two magnetic fields follow an inverse square law. So if you could cut it in half, it's potentially 4 times the rotational force per input. And that might improve that. So that's key. Now the second key would be adding a second coil. Now, technically, if you add a second coil, your amp turns have doubled, your input amps have halved, and so your rotational force is the same. It doesn't behave really that way, but it behaves somewhat that way. And with 3 and 4, I'm not even sure I'm finding any improvement, but I consistently see an improvement with adding a second coil. And a little bit of that is that you're balancing it, the force there. But it's also, I mean, it should be a doubling, but you should at least be able to get 50% more there. So better rotor, narrower air gap, 2 of these instead of 1. And now, hopefully you can get these out to like 20, 21, 22 kind of thing. If I can figure out how to add 3 or 4, it's just there's stuff going on here that I don't understand. And, maybe that'll work. Maybe it won't make things better at all. Next thing is, what if you make it go north, south, north, south, north, south? Now, for each pulse of a coil, it's not only pushing one out, it's pulling the next one in. And so doing that, I don't think it'll be a doubling, but I think you'd maybe get 50% more torque for your input. However, we've been talking about how does it behave with the air gap? How does it behave in the z-axis and so on? I just hope it's not like a completely different moonscape and like all of this, goes out the window. But so I'm going to keep it monopole and then look at that sort of later on once I have a good machine. I don't know if I had another, but I mean, aside from changing the geometry of the rotor entirely, those are the ones I can come up with. With a 6-pole thing like this, and monopolar or bipolar. Let me show you one last thing on the spreadsheet, and we'll wrap it up. So if we look here at 4 volts, it was spinning at 654 RPMs, and we were getting 4.5% back from the spike. We go to 5 volts, and that was the RPMs. We're getting 6% back, and then we load it, and then we load it more. And even with it loaded more, we're getting 5.7% back. Let me highlight that. So, I mean, if you can follow along here. So, as I was just saying, that 654 RPMs, 4.5% back, and then we go up to here, 5 volts. We have that back 6%. Now it did a little bit worse than when it was loaded, but of course you have to add in that, which more than makes up for that drop there. So it's actually better. I mean, it's best with the 2 generator coils instead of the 1 generator coil. But that 0.578 that you're getting back from the spike is higher than here, and your RPMs here were 654, and your RPMs here were 570. So again, this is not behaving anything like something on the desktop. So you're moving slower. This is better than that. So what that makes me wonder is you could just keep loading it and slowing it down. I mean, granted, this is going really slow. Eventually, you want the thing to be able to spin at 2,000-3,000 RPMs without worrying about it wobbling to death. But if you go down to 470 and this continues to improve, and this is still better than this, then it's like just keep feeding it current and keep loading it. I don't know whether that trend will hold, but you can see that's also the case here. 7.1% versus 6%. Oh, golly. 796 RPMs versus 670 RPMs. So it's slower at 1 volt higher, but this is still better. So you can kind of see what I'm getting at there is that, you might be able to just load the crap out of the thing. Okay, so, I mean, let's not, get ahead of ourselves. We've got a whopping 21.2% efficiency. That's where we're at. But we were at, where does it start? We were at 9.3% efficiency at 4 volts. We're out to 21 there. Yeah, we've got this pattern going on with the amount you're getting back from the inductive spike. So as I said, I think the thing to work on is having a little better efficiency from the generator coil. Maybe that guy from Monroe Live would talk to me. But I mean, they get 95% back. Poor me, huh? All right, so I hope everyone had fun. And you can see now also why I'm frustrated that I can't make a decent print. So once the decent print is in place, then implement the plans spoken about in terms of the air gap and getting the second coil going and things like that. So I hope everyone had a wonderful Easter, and thanks for coming along. I'll get another video out to you here at some point. It's kind of dependent on the printer a little bit. Stay healthy, everyone. Take care. Bye-bye.